if we look at this, for example, let us see, we care about mainly the fixed side. In the fixed side here, for example, this is our problem. So we care about the elements here, the element here. This element has a traction value in Tx, for example, or T1. This is T1. So we have traction before and after here. So at this node, we have traction here and the traction here. This is a traction before and this is a traction after. Okay? Here it is the same value, but sometimes we don't have the same value. But in this node, we have only one value for the node. So after and before is the same. The same here, we have traction before and the traction after. So practically, when we have fixed support like this, this will contribute to this element, the vertical element, and will contribute also to the horizontal element here and here. Because part of the traction here, you'll get traction at this point. You'll get traction at this point because you have continuous displacement. As far as you have continuous displacement at this point, that means the displacement at this point is zero. So the program will understand the displacement at this point from this side is zero and from this side is zero. So you are forcing the displacement from this side to be zero, so you will get traction. And you're forcing the displacement from this side to be zero, you will get another traction. So this traction from this side, this one. And this traction from this side is this one. You can read it in the output file. Okay? I will take this horizontal element, so we have traction like this one. So this part here it is. Okay? That means this traction can be divided. We have two ways in doing this. The first way is to break it up to geometrical shapes or to use the quadratic element equation. I will choose both. So this one here, we will have triangle, this triangle plus this parabola. This parabola here, can you see? Okay, well, let's do it by red. This parabola from here, this one here is this one. And the triangle here is this one is this one. Okay, so we'll break this into two shapes like this, and we'll end up to, okay, sorry, so this one is, sorry, this one is repeated, it's okay. So we'll end up to, so this is the first element, the horizontal element here. This is a horizontal element here. Then we care about this vertical element here. You can see here, this vertical element, I can do it by two ways. I can compute the value for subtraction using two ways. Either to take this traction and this traction, both of them are the same, so we can put them as rectangle, like this one. And we take the difference between this value and this value to put it as parabolic shape like this. Or we can do it using the shape function. We take the first one, then the second one, then the third one. The first one is triangle plus parabola, like what we did before. And the second one is parabola like this one. And the third one is triangle plus parabola. Both of them will give you the same results. So at the end of the day, you will have, as we did before, this is a cumulative slide. This is a cumulative slide. In this element, for example, this is a boundary element. I'm going to put it with a marker like this one. This is a boundary element we have here. This is the shape, and this is the last two elements which has traction. What is the purpose of that? We want to check our results. We want to check our results. We want to read our results. We read, for example, what is the equilibrium? How can we compute the equilibrium for this traction? We knew sigma the forces, the summation of the forces in x direction equals 0, and the summation of the forces in y direction equal to 0. So we want to check, we want to read the output. How can we interpret this output? So the first element, the horizontal element, we have this traction here. It is divided into triangle and the parabola. The triangle gives you this value. The value of the triangle is the area of the triangle, which is the length of the element is 1 meter. times attraction over 2, and it is applied in 1/3 of this element. So this area is 1/3. Okay, and here it is 2/3 of this value. This value always it is 1/2 of this value, which is 0.411 over 2 times the length of the element. So you will get this value and you will get this value. The same for the element here. So this element we have a triangle and a parabola, and this element, as we did before, we divide it into triangle and parabola as we did before. So at the end of the day, we have value here. It is beyond the zoom here, and we have value here for traction, and we have value here for traction. We have value here for traction. The value here is the same like here. So this one we can say it is 0.137066. So we have this value here, and we have this value here in this direction. These two values in this direction. It depends on the signs, the value on the sign, because this is negative. And we have this value. This is positive sign. This is this direction. We have this value from the horizontal element on the top of on the bottom of the problem. And at the end of the day, we have here two values, one here and one here. Okay, all of these values, this one. Okay, all of this value should be in equilibrium with the applied force. Remember, our applied force is 1 ton per meter square. This is 1 ton per meter square. So the value of the traction we get, it is ton per meter square or kilonewton per meter square. So the summation of the forces, for example, this force will have 1 ton per meter square times 1 meter here times 1 meter inside the screen. So we'll get up here, it is 1 ton, okay, or 1 kilonewton. And from this element, we have traction in this direction. And from this element, we have traction in this direction. And from this element, we have traction in this direction. So the three values of this traction should be in equilibrium with the 1 meter, with the 1 ton here. Okay, this is what we want to read. Okay, so the summation of this value, I'm going to mark it by red. The summation of this value together with this value, together with this value, together with this value, together with this value, this value should be equal to the 1. This is exactly what I did here. If you look at this, this is the force of the horizontal element here, and this is the force of the horizontal element here, and this is the force of the vertical element here. So this one, if you sum up all of this one with the 1 ton in the opposite side, this, you will get very small number here, 0.013 or something like that. Of course, every time you increase the discretization, you will get near to the sigma the forces, or the summation of the forces in the x direction equal to 0. So the first conclusion you have to understand about boundary elements, it is highly dependent on the summation. You will not get pure sigma the forces in the x direction equal to 0. This is very important. This is not like finite element. Okay, this is very, very important. In finite element, it is clear. You have sigma the forces in x direction should equal 0, because in finite element you are forcing this condition from the beginning. Okay, k times u equal p, the stiffness matrix times the displacement equal p. This is equilibrium equation. Okay,